PhD, investigating quantum communication with semiconductor quantum dots. I also want to let everyone know that these events are being recorded and they will be live on the IQuest YouTube channel. And for bandwidth purposes, we ask everyone to turn off their sound and their camera. You should please put your questions in the chat box. And Christian, hopefully it's okay if I maybe interrupt you with any urgent questions.
That's fine, yeah.
If you can maybe break a couple of times that you think are good for questions, we can do that as well.
Okay, after every main chapter, let's have a break.
If there are any, and then we can do questions at the end as well. So why don't you take it away? Thanks a lot.
All right. Thank you, Elizabeth, for the kind introduction. So thanks very much for inviting me. It's always a pleasure to present this pretty big part of our work to people also overseas. And for all of you who don't know us, we are located in Austria, in Upper Austria specifically, at the Blue Danube. And at the north of Linz, there is the beautiful campus of the Johannes Kepler University, where I am performing my PhD thesis in the group of Professor Armando Rastelli. And what I will talk about today is, first of all, I'll give you a basic introduction in an important concept of quantum communication, which are quantum networks. I will explain you why we want it, what are the basic building blocks, how we plan to realize them. Then I will go into the quantum light sources of our choice, which is our main focus in the group of Armando Rastelli, which are quantum dots based on gallium arsenide. And I will explain you the emission properties and everything there is to know about. And finally, I will come to some actual applications we performed using those quantum dots in the context of quantum communication. So first of all, when I talk about a quantum network, what do I mean by that? So a big goal in quantum communication is to establish a network of different quantum nodes. This means these are locations where quantum information can be generated, processed, stored, and to interconnect these nodes over basically arbitrary distances over so-called quantum channels, where this quantum information is transferred. And as soon as we talk about transfer of quantum information, we have to talk about losses. Because in contrast to classical information, we cannot just re-amplify quantum information which is lost in some channel. So for that reason, one major block of a quantum network is some kind of quantum repeater. This means some in-between system which can re-amplify quantum information to distribute quantum information over arbitrary long distances. And one special kind is the photonic quantum repeater. Photonic because photons are pretty convenient due to their robustness against environmental decoherence and due to the established links we have already on the world, like the optical fiber networks or free space over satellites, for example. And photons, single photons, have several degrees of freedom, which we can use as carriers of quantum information. We, for example, focus on the polarization, which forms a qubit. But there's also orbital angular momentum. There's also time bin. There are several degrees of freedom you can use for the transport of quantum information. And what we then need for such a basic quantum repeater is, first of all, we need bright sources of a regulated stream of entangled and indistinguishable photon pairs. This is quite a mouthful, but I'll explain what I mean by that. So first of all, these sources have to emit photons which have a very high entanglement with each other. This is the basis of this whole concept. And then two photons of these two pairs perform with each other a so-called Bell state measurement. And for this Bell state measurement to succeed, we need a high degree of indistinguishability. This means these two photons have to interfere, in the easiest case, just on a beam splitter, and detections, clicks are here detected. And this only works if the indistinguishability is very high. So these photons are the same in every sense of quantum mechanics. And what this does is if we detect here a Bell state, for example, the psi minus Bell state, then this heralds entanglement on the outer photons. This means we established an entanglement between two photons which had nothing to do with each other in the first place. So this is the basis of distributing quantum information, or specifically entanglement over long distances. In reality, there's one important ingredient missing, which we'll touch on only a bit in this talk, which are quantum memories. Because you actually have to store these qubits here in memories to have them available deterministically on demand. And they also serve as a kind of redundancy to drive protocols, which really bring down the losses in such systems. And then when you have this entangled photon pair over a distance, excuse me, you can, for example, perform applications like quantum key distribution or distributed quantum computation and so on. And when we talk about photonic quantum repeaters, the question arises, what sources are actually out there? What can we use? One very common source of single photons are coherent states from attenuated lasers. These are cheap, these are easy to implement, but they have the major drawback that as they are coherent states, they have always a probabilistic distribution of the photon numbers. This means if you have one photon, there's always a finite probability that you have also two or three, and this spoils a lot of concepts in quantum communication. And also entanglement is not straightforward to generate from such sources. A much better powerhouse is the spontaneous parametric downconversion, which is heavily used. They have advantages like they're operable at a wide range of temperatures. They deliver almost a perfect degree of entanglement of their photons. And they are well established. People know how to use them very well by now. But they have the fundamental drawback that also they have a probabilistic photon pair distribution. This means the harder you pump such a crystal, the higher the probability gets that you have more than one photon pair. And this again brings down the success rate of such quantum repeaters, and therefore also the overall entanglement of the final photon pair. So the solution by that is provided by semiconductor quantum dots. This is our main research focus. So semiconductor quantum dots on a very high level are nanostructures of one semiconductor material within a big host material of another semiconductor material. And if you choose the materials well, what you arrive with is an energy structure, which resembles very much the textbook quantum well. This means you only have discrete energy levels within this quantum well. And here in this quantum well, charges can be trapped. Like in a simple case, an electron and hole, which is bound by Coulomb interaction due to their vicinity. Here, for example, you see such an exciton wave function in the absence of any outside electric fields inside such a structure. And what happens is that this electron and hole pair will eventually decay radiatively by emitting exactly one photon. And the interesting part is now that in order to emit another photon and this from this configuration, the exciton has to decay first and can then be repopulated and then can decay again and so on. And what you have is an autocorrelation which is basically zero. This means that you have a photon turnstile, one photon after another, a regulated stream. And this gets rid of this probabilistic photon number distribution. And quantum dots by now have quite some history. So after the discovery of the single photon emission behavior, people found out that these pretty much afterwards that the quantum dots can only also used for entangled photon generation, and that these photons are to a high degree indistinguishable. And from there on, a lot of material research happened, and then we managed to combine everything so that the source delivers highly indistinguishable and strongly entangled photon pairs. And by having that, we performed some basic tasks, some basic primitives of quantum networks, like lately quantum cryptography, and also this entanglement swapping process, which is the foundation of distributing the entanglement. And also some people, not us, but other groups, for example, in Cambridge, they also use the exact same quantum dots as basic quantum memories. So we actually have all the building blocks already individually shown, and it's a matter of combining all of them. And I will go into greater detail about these two works and also a bit about the quantum memory then in the last chapter. So I think this is a good spot for questions, because this is the foundation basically of the quantum repeaters.
So there are no questions in the chat, but I was thinking I could ask a quick one. So are there any fundamental limits on the purity and indistinguishability of photons from quantum dots? I guess what I'm thinking of is there's always a double excitation possibility, and it's going to depend on things like your excitation pulse time and then the bandwidth and all of that. Because I guess my point is that with SPDC, if you had perfect number resolving detectors, there's some fraction that you could get that are single photon entangled pairs out of your SPDC. Is there some like fundamental limit for quantum dots?
There is, but it is not the re-excitation what you mentioned, because this is in this cascade quite limited, which I will show you in a moment. But there is another very intricate detail in such cascades, which you will also see in a minute, namely an unwanted entanglement in time when you have such a decay system. And this is indeed fundamental in the sense as long as you have constant radiative lifetimes. But when you, if you're also able to tune that, I will also show how we plan to do that, then you can overcome this limit. Then, of course, at a certain point, you will reintroduce re-excitations, but still the fundamental limit of standard samples can be overcome. This is also a big task, which I will show you now.
Great, thanks.
Okay, any further questions? If not, then I will continue. Good. So now I will explain you the sort of quantum dots that we are working with primarily, which are based on gallium arsenide. And I will explain you what the advantages are of this material system and what emission properties these quantum dots have, which can then be useful in quantum communication. So first of all, we produce our quantum dots with so-called molecular beam epitaxy, where we grow a layer of aluminum gallium arsenide as a host, and then we distribute hot aluminum droplets on the substrate, and these droplets etch nanoholes into the host material, which are about 50 nanometer lateral and about 5 to 6 nanometer in depth. And most importantly, the symmetry in plane of these holes is very high. You will see in a moment why this is so important. And then we fill the hole with gallium arsenide, which then actually forms the quantum dots, and cap everything again with aluminum gallium arsenide. And what comes out is a wafer with many thousands of quantum dots, which can then be cut in to whatever dimensions we need them for certain applications. So after the growth, briefly, I also wanted to show what we can do. We have a big advantage in Linz that we have basically most of the needed infrastructure in our campus, which means we can grow the sample, we can characterize and post-process it, and then we can use the final samples and structures for spectroscopy and actual quantum optics experiments. This is a big advantage. The the most basic operation we can do is that we put the sample in a cryogenic environment, 4 to 10 Kelvin. We focus a laser on one quantum dot with a micro-PL setup, and with a laser power which is larger than the band gap of this bulk material where the gallium arsenide dot is embedded in. And this generates a lot of electron holes, which are then scattered into the quantum dot. And when these different configurations recombine, then we have a bunch of lines in a micro-PL, which we see here. So the most dominant is the transition of the excitons. But as you see, there are much more complicated quasi-particle structures possible, which can radiatively combine and give us these transitions, these rather sharp lines. And when we look now in the wavelength domain, and we focus, for example, only on this neutral exciton transition, and we look at different dots on a sample, then we have this kind of distribution. So this means the center wavelength of this quantum dot is not always the same. It has a bit of a distribution, which has implication for the scalability, but we have countermeasures for that, which I will show you then. Of course, this non-resonant excitation is not particularly useful for actual applications. What we instead do most of the time here is we do not excite the exciton, but we excite the biexciton. The biexciton are 2 electrons and holes, so we have a full shell in this lower allowed energy levels in the quantum dot. And we do that, so we address this biexciton by a so-called resonant two-photon excitation. This means we use the fact that the biexciton, so the energy of the biexciton, is not exactly 2 times the energy of the exciton, but it is a bit lower because of correlation effects. It basically gives you a binding behavior, so the energy of the biexciton is lower. And this means that we can tune a laser, a pulsed laser, to exactly half of the biexciton. And then by a two-photon absorption process, 2 photons from the laser field get absorbed and directly address the biexciton. When we have this biexciton, it will eventually radiatively decay with a statistical time of about 120 picoseconds in the easiest case. And what is left is then one of 2 allowed exciton states, depending on the spin state, so electron up and hole down, or electron down and hole up. And when the symmetry of the confinement potential here is perfect in plane, then these 2 energy levels are degenerate. And because of the conservation of angular momentum, these 2 spin states can only be reached by emitting a right polarized photon or a left polarized photon. Then eventually also the exciton will decay with a radiative lifetime of 230 picoseconds. And then again, to the conservation of angular momentum, only the opposite circular polarization is allowed for the second photon, which is emitted. So when we only look at the photoluminescence, now it looks much cleaner. We only have 2 sharp lines, the exciton and the biexciton, displaced by 2 nanometers in wavelength. And most importantly, if these 2 branches here are completely indistinguishable, then we have a perfect entanglement in the polarization domain between the exciton and biexciton photon. So this is the basic mechanism how these entangled photon pairs are generated in our dots. And of course, now I mentioned that this is only the perfect case when the 2 energy levels are degenerate. But in general, this symmetry is not always perfect. And what this does is, if you have an elongation in one direction, you open here so-called fine structure splitting, so the 2 energy levels are different. And this means also the transition energies from the different branches are different and makes it distinguishable. Actually, for very high fine structures, you see that in a polarization resolved spectroscopy, that you actually have two lines appearing depending on the polarization angle. But now the aluminum droplet edge comes into play, because when you do it right, the fine structure splitting by itself can be as low as on average 2 to 3 micro eV, which is in the order of the natural line width, or most importantly, even below. So there's always a relatively high probability to have quantum dots with 0 fine structure splitting on your sample. And this means that we can get rid of this additional phase term, which is introduced by the fine structure splitting, because this cancels out. And with a bit of search, we can have photon pairs with a fidelity to the ideal Bell state up to about 99%. But of course, searching around on one quantum dot is not particularly helpful in many cases. So what we're also developing and keep on developing since years is an approach to restore the symmetry deterministically on any quantum dot by strain tuning devices based on piezoelectric actuators. So what we do is we place our sample on a piezoelectric actuator with 3 independent pairs of, we call them legs. And by applying individual voltages between the grounding on top and the leg pairs, we can apply strain in 3 independent directions. And this is enough to restore the in-plane symmetry of the confinement potential, because we basically squeeze it or stretch it in any direction we want. And because you have all the freedom over the anisotropic and the isotropic strain in the material, you can not only bring down the fine structure splitting to 0 for any given wavelength, but we have an additional degree of freedom to also tune the wavelength. So this is important if one wants to interface, for example, 2 quantum dots, that the energy matches and they have both 0 fine structure splitting, for example. So, okay, this is the basic mechanism how entanglement is generated and how we do it deterministically. But very important is also what are actually the emission characteristics. What about the brightness? What about the regularity? So in most use cases, in the simplest cases, we use this relatively simple sample structure where the quantum dots are embedded here in a structure with several distributed Bragg reflectors epitaxially grown below, and a few top layers, and a solid immersion lens on top. And when we then drive the biaxiton with laser pulses with a length of about 10 picoseconds, what we see is when we vary the laser power as we drive a quasi-resonant two-level system, that we have these Rabi oscillations. So this is a proof or a good evidence.
Uh-oh. Looks like we lost him.
Thought it was just me.
Oh, we lost him completely now. Oh, Christian, are you back? You're muted now?
Yeah. Sorry for that. Was it on my side?
Yeah, we lost your slide share.
Mm-hmm. How much did we lose?
You were starting to talk about the double Rabi oscillations in the exit.
Okay, so not so much. Sorry, since yesterday we have quite some problems with the network. I hope that this doesn't occur anymore.
You gotta flip your screens. You're on your preview screen.
Okay, so then a second.
There you go.
So share screen. I need this one. Then I have to swap.
There you
Yep.
go.
Now we
Great.
should be back. Quite some routine meanwhile. Okay. We were here, right?
Perfect.
Okay, so sorry for this little interruption. So what I wanted to tell you, as we drive a two-level system, what we see is if we vary the intensity of our pulse laser, that we see this oscillating behavior. And this behavior is damped because of phonons. This means you lose the coherence of the excitation the longer you drive the system or with higher pulse areas. So when we operate the system on the so-called pipe pulse, where we have the maximum, we can obtain a 91% pair generation probability. So we generate a photon pair with a very high probability. And importantly, independent of the rates, how often we repeat this process, people in Stockholm have measured with superconducting nanowires with very low dark counts that the G20, so the probability to have more than one photon pair per cycle, is in the order of 10 to the minus 5. So this means that we really have a regulated stream of entangled photons, where some are missing because of in this case, pretty low extraction efficiency of 11%. But most importantly, for most cases, is that we almost never have two or more pairs. And this is basically the question also Elizabeth was asking: is there a fundamental limit of that? The thing is, we can drive this system basically as fast as the radiative lifetimes allow, because the excitation laser pulse is much shorter than the full cascade. This means in order to re-excite the system, we would need to have the quantum dot in the ground state. So as long as this ratio between the lifetimes of the cascade and the pulse laser is reasonably high, in this case, we will have very low re-excitation. And we can, in this configuration with this radiative lifetimes, drive the system with about 500 megahertz, in theory, I would say, and 320 megahertz were used by our collaborators in Rome already. And okay, this is all well and good, but of course, this 11% extraction efficiency is not very suitable if you want to interconnect several sources, because the success probabilities just drop into the basement. So what we are heavily investigating at the moment is to embed our quantum dots in advanced photonic structures. One of the most promising out there at the moment is a circular Bragg grating, which was shown to bring up the photon extraction efficiency from this 11% up to 85%. And additionally, can induce Purcell enhancement to bring down the radiative lifetimes. So this means that the excitation rates could go even up to gigahertz, if you are careful about re-excitation. This is true, because then you have this counterplay between excitation rate, so radiative lifetimes, and G2 again. So the very nice thing about these Bragg reflectors is that they do not have to rely on high Q factors, but they go in the denominator, so to say, and have a very low mode volume. To this very broadband behavior of high collection efficiency, while also have still a relatively broad band of Purcell enhancement. But this rather selective behavior of Purcell enhancement is something we also want to use to advantage, which we will see later, because the width of this peak can actually be designed by the dimensions of these trenches. Okay, now it's time to have a look how the gallium arsenide quantum dots actually perform against the spontaneous parametric downconversion sources. So here you have a relatively old but chart of different fidelities to maximum entangled state over the photon pair source efficiency. It's from 2017, but it's still sufficient to bring home my point. Namely that when you look here at the record holders to this point, these are all parametric downconversion, but you see here already a trend, and this trend is exactly comes from the fact that you drive the system. So the higher your photon pair source efficiency gets, the higher your 2, 3, 4 photon pair contribution gets, and therefore your fidelity drops. And with one work, we already surpassed here by a small margin this hard line for SPDC sources. And basically why we are here is because of exactly this 11% extraction efficiency, which bring us down to 1% pair extraction efficiency. In this first work with these Bragg reflectors, people brought up the efficiency, but they could not manage to bring the fine structure of their quantum dots low enough to get higher fidelity. So this is why we're now working on combining these two systems. So we want to place these Bragg reflectors on piezoelectric actuators and could possibly reach up this point here. Okay, it's time for a little recap here. What have I shown you so far for the source properties? So we have a reasonable brightness, which we seek to increase. We have a high single photon purity. We have a high degree of entanglement, but there's one property which I did not talk about so far at all, which is the indistinguishability, which is very important for the success rate of the bed state measurement later. So how do we characterize the indistinguishability? We do this in a so-called Honger-Mandel-like experiment. The Honger-Mandel effect says that if you have two photons impinging at the same time at the beam splitter, and they are completely indistinguishable from each other, they can, due to negative quantum interference, destructive quantum interference, only leave the beam splitter at the same output at the time. So in reality, how we do this is we doubly excite one quantum dot with 2 pulses in the temporal distance of, for example, 2 nanoseconds. And then we split the signal up. We have the late, for example, exciton in one branch and the early exciton in the other. And we delay the early one so that they impinge at the same time again at the second beam splitter where the interference happens. And then we look at coincidences between these two detectors. And ideally, we should observe no clicks at the same time because we only should have this bunching behavior at one output. In reality, it looks like that we do have coincidences at 0 time delay, and we cap out this configuration at about 65% visibility of the interference. And of course, we were wondering for quite some time why it is not 0. Is it are there phonon-induced decoherence effects and so on? And it turns out that this problem is known since quite a while from people from atomic physics. They also deal a lot with such decay cascades. And the reason why the visibility seems to have such a hard limit because the bi-exciton photon will always come before the exciton photon. So what happens in the spatio-temporal domain is that these two photons share a mutual entanglement in time. And this brings down their overall purity if you trace out the other photon of the partner. And this means that they lose the indistinguishability to a certain degree. And this maximum visibility which can come out is governed by the ratio between the radiative lifetimes of the pi exciton and the exciton. This means we rather want to have a very fast decay of the pi exciton and relative to that slow decay of the exciton to the ground state. And here again comes this the circular black grating into play, because there we want to actually exploit this asymmetric behavior of Purcell enhancement and design the cavity in a way that the pi exciton resonance lies exactly at the maximum. So we speed up the decay from the pi exciton while keeping the exciton more or less unaffected. And this is an approach to bring up the maximum visibility. Okay. What I showed you here was the interference of two photons coming from the same dot with a temporal distance of 2 nanoseconds. But if we want to do this for individual dots, which we also did, we have to look how the visibility behaves there. So what we did is we excited two quantum dots with the same laser pulse in a phonon-assisted resonant excitation scheme. This has the advantage that the actual binding energies, the actual energy levels can be a bit different between the quantum dots, and we can still excite them both. So what we did is we tuned the emission energy of one quantum dot with a monolithic piezo to match exactly the wavelength of the first quantum dot to enable this interference on the beam splitter. And what we observed is that by any means we could not exceed 50% interference visibility. And of course the question why it is not 65%, but it is even lower. And the reason for that is whenever we have solid states, we deal with impurities in the material. And in particular for quantum dot, which is important, is that we have some kind of spectral wandering of the emission line over time because of fluctuating charges in the surrounding. Because charges can be trapped by impurities, they can thermalize and be recaptured, and this gives you a jittery electric field, which shifts the emission line probabilistically in the easiest case in such a Gaussian manner. So we recorded this by a technique which is actually pretty well known for chemistry, and we adapted it for single quantum emitters. It's called photon correlation Fourier spectroscopy. And by this method, we can set an upper and lower bound of the line width for different time domains. So this means we can look at the indistinguishability, or we can estimate the indistinguishability for photons which are emitted in a very short temporal distance, which corresponds to this interference from one dot, doubly excited. And we can also look at the regime for very high timescales, basically up to infinity, which is related to the indistinguishability from different quantum dots, because these two different quantum dots have never had a mutual correlation in their central lines with each other. So they feel all the noise basically. And so we had an indication about the noise spectrum in the samples, and this allowed us to grow new batches of quantum dots, which are basically flat. So this means we have now a line width which are in the order of 2 times the natural line width, which we still seek to improve, but it's a good start. And with that, we want to restart this business of interfering multiple quantum dots with each other. Okay, so to sum up the properties, again, we have no high efficiency yet, but we know how to achieve them. We have a very high single photon purity. We have a moderate indistinguishability, where we know where the limit comes from, and we have a high degree of entanglement. So the conclusio here in this chapter is we need to go away from the simple cavity structures more to different photonic designs. This is only one of them. We have more ideas, but this is the most promising in my opinion. And then we can really have green checks everywhere at one point. I think this is a good spot for questions before I come to the application. Great,
because I have a question. So the spectral diffusion that you were just talking about.
Yep.
You said you grew samples with less spectral diffusion. How did you do that?
Yeah, it's actually not so trivial. So in the end, it all comes down to purity, because when you have material where you have grains, for example, of gallium, then these are basically again quantum dots. So they can trap charges and enable this fluctuating behavior. But if you have an infinitely perfect crystal in all directions, you don't have that. You have a perfect band structure, you have your perfect quantum well with nothing in the surrounding. So it's basically, it comes down to purity. There are other measures to mitigate this spectral wandering. For example, if you speed up the radiative decay, you can see it in different pictures. You basically enhance the natural line width, so the spectral wandering doesn't affect you so much anymore. Or in the time domain, you can see that your wave packets are shorter, so they don't have so much space to decohere. It's equivalent with two pictures.
Great.
But yes, growth is the greatest factor.
So Paul has a question about growth. He's wondering if you can go to longer wavelengths by making the dots bigger.
Yes, we can. There is a limit, because at one point these dots become again asymmetric. But I have to be very careful here, because I am not so much into the growth itself. But you can do this, but there is a limit, but I'm not sure exactly where it is. We can definitely not go to telecom wavelength or something like that. I think the highest we ever got was something like 820, but this was more an accident. So we never really tried to push it really high. This would be actually a question for Armando. Yeah?
So I have a question about Purcell enhancement with your system. So your two photons are about 2 nanometers apart.
Yeah.
And obviously, I think maybe obviously, maybe not, there's a limit to how much you would ever want to Purcell enhance when you start to get some overlap between two photons, because then you have nowhere to pump. Right? Is that a true statement, or am I thinking about this wrong?
Yeah, this is true. You really have to look at the Fourier line width. The lines will be broader, but this is still far away, because that's actually an interesting thing at one. But I think at the points where you have to worry about the spectrum, you worry more about re-excitation already, because then also your pump pulse has to be already spectrally very broad, and then everything gets the best. So there's a trade-off to make.
I mean, that was kind of where I was going with this. So do you know what that Purcell enhancement kind of limit is, of what the order is, before you start to kind of have no way to fit your pump in there without re-exciting?
No, but this is actually something we could relatively easy model. I just didn't do it. I just always said, okay, you have to be careful. There's a trade-off, and then it's over. But it would be really interesting to really calculate it, the behavior as a function of the Purcell enhancement. And it's actually a good idea. I should do this.
Okay. And we have another question from Tiffan, and I don't understand your question actually, so maybe you want to unmute yourself and ask it yourself.
Yeah, thank you. Hello, Christian.
Hi.
It's more maybe something that I missed, but when we do SPDC, either using, for example, a cavity, when you have a cavity, then the output light would be monomode spatially, because the mode would be constrained by the mode of the cavity. But then you can have you can be multimode spectrally. And I was wondering, when you use the quantum dot, do you consider this matter in the designing? So do you have a spectrally multimode structure in HPDC light, or do you have a multimode structure, especially? Did you consider this question, or you don't have this problem at all?
So spatially, we also have this problem. This is true because when we talk about efficiencies, we often talk about the efficiency of extracting the photon up to the objective. But what is actually much more interesting is, Elizabeth is already laughing, is how well you couple these photons actually into fibers, and especially single mode fibers in most applications. So the mode structure, the spatial mode structure is mostly governed by the cavity structures we have.
Okay.
And it's actually not really straightforward to structure your cavities to have really a Gaussian mode. People like Richard Warburton in Basel did this really well. They made some Gaussian-like top DBRs and directly couple it into fibers. So they reach efficiency in the fiber, actually on the detector of 50%. So they have up to 100 megahertz of photons in the fiber. This is an issue, yeah.
Okay.
I was nodding because some people here have heard my rant about how photons aren't photons until they're in a single mode fiber.
Yeah.
So Ujan has his hand up. Ujan, you have a question?
Yep, thanks, Elizabeth. So here from the max visibility expression, is basically to increase it, I would want the denominator on the fractional term to be as high as possible. And I was thinking, is that engineerable in your system? Like, is the single exciton decay, is that just a spontaneous process, or do you have some degree of control over it?
So in the first approximation, this is just a spontaneous decay, yeah. There were people in Stockholm on Paderborn, which are currently try to make this basically stimulated. So they want to stimulately depopulate the biexciton. And another approach is coming from the other direction to make the exciton artificially longer. So what you can do, for example, if you filter the exciton line spectrally, what you do is you make the, let's say, the effective lifetime, which you see in your setup, longer. So this means you mimic a higher lifetime of the exciton. This is another approach, but this is the more lossy version, because then you first of all, you lose photons, of course, and you limit yourself in the excitation rate, because you have more uncertainty in time on the exciton. So the most promising approach, therefore, that I see is, from among all these, is this designing of the Purcell enhancement in such Bragg reflectors to speed up the biexciton decay, to bring this term here to lower values and have an overall better visibility. So we from simple estimations, the Purcell enhancement, I think, of 3, we could already achieve a maximum visibility of about 90%.
Got it. Thank you.
Welcome.
So I'm going to ask another one, because now people keep reminding me of questions I have.
Oh yeah.
Is there a dark exciton somewhere? So, and can you get an energy level scheme where you have the lower one's a dark exciton and the other one's not?
There is a dark exciton, which is energetically normally, I think, a bit lower with respect to the excitons. But under these normal conditions in our setups, like at 4 Kelvin, we normally do not get into the dark exciton as long as there is no mixing because of some high strain, something like that. We know that we can create a mixing between dark and bright exciton under some circumstances. We can even create mixing between heavy holes and light holes and so on. But in this case, we do not care so much about the dark excitons because they are, as their names say, they are dipole forbidden. So we do not really observe losses into these channels. But there are people who actively use the dark exciton because they are so long-lived. So they use them as long-lived qubits, actually. They address them, let them precess, and then excite into the bi-exciton state, let it decay, again, excited. And they have this is for example, what Gershoni does. He calls it the entanglement machine gun. It's a very sensitive name.
That's what I was thinking of, yeah.
Yeah.
But you say you have a way to mix it. Wouldn't that lengthen the lifetime of your exciton if you mixed in a little bit of the dark exciton?
You would see it in a lifetime trace, I would reckon, as a very long background or tail. So you would not see it directly in a lifetime measurement because they are so much longer. Depends how long these radiative lifetimes really are, if they even radiate, and where they in which spectrum, which line width they radiate, or if they switch back by some mechanism to the bright state, right? This all it depends on all of these factors if you would even observe a different lifetime than on this one line in the spectrum.
I'll talk to you more about this when we talk after. Paul is also sitting patiently with his hand up.
Okay.
I don't know if I'm patient. I'm just wondering whether or not the metastructure, the bullseye pattern, can be used to help shape the mode so that you can better match your Gaussian mode, even if the normal emission pattern is not that. But you certainly have the ability to do something transversely to the mode that's coming off with that structure. Yeah,
it should. You should have pretty much all degrees of freedom to make it Gaussian. But then it's a matter of how well you can really etch the trenches, how uniform the spatial distance is. There are a lot of things into play.
Do you have to worry about polarization effects on that? So that, because on some polarizations are perpendicular, on one side are perpendicular to the structure, and on others are parallel to the structure. I could imagine that changing quite a bit, actually, what the mode looks like depending on the polarization.
Yeah. So one of the major problem was actually that first, because it's very important to get it perfectly circular. As soon as you have an asymmetry inside, you split the mode into two orthogonal modes. Yeah, this is true. And this is something we saw frequently, or when I say we, I mean more people in my group who do this work really from the processing side and from the characterization side. And one major issue is exactly this ellipticity. So you really have to go already from the e-beam lithography side. You have to be very careful to get the symmetry right, and then also during the etching, that the mode splitting is not an issue.
Great, thank you.
We should let you finish up your talk.
Okay, if you have some more time. And I will continue. So now for the last chapter, I will show you some actual applications of this quantum dots in the context of quantum communication. So we tested some standalone building blocks of this photonic quantum repeater in the form of entanglement swapping. This means we heralded entanglement at a distance, of quantum key distribution, which is an actual application for symmetric key generation. And I will touch a bit on quantum memories, because we are recently also collaborating with people in Cambridge, and they can also be realized, at least this is the aim, with quantum dots. So during my stay in Rome at the beginning of my PhD, we performed entanglement swapping. And what this means is when we have one quantum dot, which we doubly excite in this case, we get an entangled pair, which we call the late pair, and the early pair. And when we write down the equation of all 4 photons evolved in the polarization space, we can construct it in a way that we use the Bell states, the 4 possible Bell states, as a basis. This reads like that. So with that in mind, what is now important is how the 2 photons here, the inner photons of the 2 individual pairs, behave when they impinge at the beam splitter. And we assume that they were initially, when they impinged, at the 4 different possible Bell states. And here it is important to look at the statistics of the Bell states after the transformation at the beam splitter, because we see that the psi minus plays a special role, because it is the only one which produces bunching at the detector. This means it's the only one which brings us the photon at one and the other output, and it gives us a coincidence. All the others do the opposite. So this means in this in the simplest form of Bell state measurement, whenever we have a double click, this heralds us that we measured that we had a psi minus Bell state at the input, so we can project down this whole state into a subspace, and we know immediately that the outer photons, in this case 1 and 4, are also in the psi minus Bell state. So what we can do is we can watch for heralds, for clicks from the Bell state measurement, and whenever the entanglement is heralded by a double click, we perform full state tomography on the remaining 2 photons in which state we're interested in. And we found that when we do this, we get a fidelity to the ideal psi minus Bell state of about 58%, which clearly violates the classical limit. And we also know why it is not perfect, because as I already explained, the visibility of the interference at the beam splitter depends a lot on the indistinguishability. And we know that we are, with this simple sample structure we use there, we are limited to about 65%. So this gave us the upper bound for this process. And this is why we think that with these approaches, by speeding up the biexciton will dramatically help you. And okay, for the sake of time, I will skip over this assessment because we made some calculations how far we could really go with these approaches. But for the sake of time, I will go over this and come directly to the next application which we did, namely quantum key distribution. So first of all, I will explain you how quantum key distribution with entangled photon works. What we did is we placed one quantum dot in our lab and led one photon, I mean the excitons, to one side, which we call Alice, and couple the biexcitons into another fiber, which leads over 350 meters to another building, where another receiver box named Bob is located. And what is now happening is that, for example, if we have a photon here at Alice, we have here 50-50 beam splitter. This means that we have a perfectly random choice if the photon is going this direction or in this direction. And then these 2 directions correspond to 2 different measurement bases. So here, for example, the photon is analyzed in the horizontal vertical basis. And in this arm, it is analyzed in the diagonal basis. And now what happens is that Alice and Bob just measure their impinging photons one by another and write down their basis in which they measured and their outcome. So if they have a click on this and this detector, which gives us the symbol. And then in the so-called key sifting phase, Bob sends over to Alice only information about in which basis Bob measured. Alice compares then her basis with Bob's basis, and if they coincide, she puts her measured symbol into a key register and tells Bob to do exactly the same without ever sharing the measurement outcome. And what now happens is that due to the entanglement and due to discarding the unequal bases, we have an equal key on both sides without ever sharing any sensitive information on the public channel where everyone can listen. And compared to the famous single photon BB84 protocol, this has several advantages, namely that the choice of bases is perfectly random by nature. You don't need a quantum random generator, a random number generator to choose the bases. Then we are more robust against so-called intercept and resend attacks, because if some adversary listens here on the quantum channel, on the photon channel, and splits off some photons, there is no information contained. So there is nothing he could extract here. And for us, very importantly, this scheme can be embedded in a quantum network, which is not the case for single photons. So this safe key, which is then created on both sides, can then be, for example, used by encrypting in a one-time pad to have a perfectly information-less encrypted message, which can be safely sent over the public channel, and then be reconverted by a simple, again, the same simple XOR operation on Bob's side with his key to recover the decrypted message. And we did that with a raw key rate, an average of about 135 bits per second, which is mostly limited by, again, extraction efficiency, losses in the fibers, and so on, and an average qubit error rate of 1.91%. This means that we could, after a so-called reconciliation process, where error correction happens and privacy amplification, we could distill 86 bits per second out of it. And most recently, just to go very quickly over it, we did the same also at temperatures of 20 Kelvin with a diode structure, which has several advantages. Namely, first of all, we have full control over the charge environment in the dot. This means we also get rid of behavior which is called blinking. Because in ask-zone samples, in normal samples, you always have a probability for charges to drift inside the dot and change its energy structure and block basically the excitation and make it optically inactive for some time, which is usually quite long. So if 2/3 of the time these samples are basically off, but with the diodes we can control the charge environment and completely get rid of this blinking behavior. And under these conditions, we also checked how well we can perform QPD. And we ended up in a lower qubit error rate, which is basically caused because of we don't have this cavity perfectly under control. So the extraction efficiency is even a third or even an order of magnitude lower than the previous samples, which is under investigation. But most importantly, the qubit error rate is higher because the entanglement drops, which is an interesting physical endeavor by itself to really know where it comes from. And we ended up still with a finite key rate of 14 bits per second. And now I will only very briefly touch the quantum memories, because they are also an important building block of our quantum repeater. And interestingly, people from Cambridge in the group of Mete Atatürre, they have already used indium gallium arsenide quantum dots. And what they do is they generate a single exciton in a in a coherent superposition of a spin state. And by hyperfine interaction, they were able to couple this spin to the nuclear spin ensemble in the quantum dots, which is then a very long-lived system. This means that as soon as they couple this electron into this nuclear environment, these superposition lives very long and can then be read out back to the electron, and then, for example, be read out optically. So this is something which will basically be my main topic for the next years, together with this group. Without going too much into detail here now, just to let you know that these things exist, and people already showed that gallium arsenide quantum dots show about 100 times larger coherence times of this electron qubit, which is a huge advantage. So there's a lot of research going on in this direction now. Okay, so with this, I will sum up. So I showed you our highly symmetric gallium arsenide quantum dots with a high degree of entanglement and almost zero G2. The indistinguishability is currently limited to 65%, but we know exactly why. And I showed you some basic primitives of a quantum repeater, which were individually shown. And of course, now the big long-term goal is to combine these concepts, to have very bright and entangled and indistinguishable photon sources, to perform entanglement swapping to entangle at a distance, perform quantum key distribution with this basic repeater, and bring also quantum memories into play to really have a full repeater scheme. But this is really a long-term goal. And what we're also researching is if we can, for the sake of scalability, combine all these concepts I showed you. This means the strain tuning of the Bragg reflectors with a pin diode to have an additional degree of freedom, to also independently tune the binding energy or the energy of the biexciton-exciton individually, while having this nice blinkingless property. And also we are investigating, together with the University in Vienna, the benefits of quantum dots and different excitation schemes on the security aspects of other quantum cryptography primitives. And of course, we're also interested, just to go very briefly over it, we're interested also in entanglement at even higher temperatures to bring it in reach of common Stirling coolers. And of course, what is also important is the wavelength in typical channels like free space and optical fibers are well known to have a sweet spot at the telecom wavelength of 1,550 nanometers. So we are also investigating the different approaches to convert the wavelength to this regime, and other groups are even investigating different material systems which emit already natively at this wavelength, or even transport this droplet etching technique to a different material systems which emit then at C-band, at telecom C-band. So thank you for your attention.
Thanks, Christian. That was great. So we had a lot of questions during the talk. I don't see any more questions in the chat. Does anyone else have anything for him right now? Otherwise, we can get on to our meetings. No? All right.